Excellent. All right, thank you very much. Yeah, as Ryan said, I'm going to be talking about OT, ICS, SCADA, whatever you want to call it. This is some work that my team at work has been doing, and I thought it was interesting. So even if it's not directly applicable, I think to what you do, I think there will probably be maybe some ideas that might inspire you. As you said, I'm from Canada and moved to Norway because apparently I'm fond of cold places. Working for an OT security startup here called Omni, and so you've heard me throw this word or this acronym around a lot at this point. What is OT? So if you're not familiar with it, OT or operational technology is basically anytime that you have computers and digital systems interacting with the physical world. So maybe that's in a factory setting like this. Maybe that's in with some medical devices. Maybe you've got like a big robot trying to catch your enemies. And it has a lot of similarities to IT security, but also a few things that are different. Similar to with the medical stuff that we just saw, a lot of it's very old, hard to patch, not necessarily designed with security in mind, and that can lead to some interesting challenges. Particularly what we were looking at was context and visibility for risk assessment and for incident response things. So in a lot of these networks, they were built like 20, 30, 40 years ago. So maybe you have some network sensors that you can see, your standard like IT things in the network, but there's going to be gaps there. And if you're an incident responder and you see an alert come in on an IP address, maybe you see that it's critical, but you don't really know why. You see that, but it's fairly opaque. And so we were trying to figure out, is there a good way that we can provide some more insight into this and maybe show someone who's responding, well, is this something that I really need to care about? Is this controlling, like the main drill on like an oil rig or something like that? Or is this controlling like the AC unit in the break room? If you're an incident responder, that can be kind of handy to do. Or the other sort of thing that we were trying to do here was help with some risk assessment, because if patching is really hard and patching is expensive, you want to really focus your efforts where it's going to have a meaningful impact. So what we found was that these network sensors are really good for the IT stuff. They can tell you there's we see this service is running on this IP address. It's got this vulnerability. Not so good for showing you what that thing was actually doing. And that's where we started looking to some alternative sources. So for the example here, maybe we can see that there's this controller thing, and we might have some guesses as to what those wires are going to, but we're not quite sure. So where can we look to try to fill in these gaps? And as you might have guessed from the title, the answer turns out to be a lot of docs. There are some other tools that we have as well. You can go to the site and actually walk around and see. Maybe you can do like some Nmap scans or something like that. Though in OT, you have to be kind of careful with that because, again, a lot of these systems are very old, very brittle. Something as simple as running a scan too aggressively could knock the whole thing over. So you want to be careful with that. You also might interview some site experts. But again, these guys are very busy. It takes a lot of money, a lot of time. And so we wanted to try to build up as good a model of the site as we could before going to these sort of more expensive methods. And for that, we turned to docs. So our plan is to convert these docs into a machine-readable format, build a graph from them, which I'll talk a bit about what we use that for, and then use that to answer some questions either about risk assessments and trying to pinpoint where we want to spend effort, or on helping give incident responders an idea what they're dealing with. There are a few types of docs that we'll go over in specific. Some of them you're probably familiar with, things like network diagrams or risk assessments or functional specifications, which are basically just like a Word doc describing how the system is supposed to function. Others are a little bit more specific to the sort of physical realm. Things like P&IDs are piping and instrumentation diagrams, and they look like this. Each one of those icons there represents an actual physical, either like a valve or a tank or something like that. and then the lines are going to be frequently like pipes between them. And so this is laying out how the whole process, the physical process, is going to work for that particular part of the plant. And there's a lot of good information that we can pull out of these. In particular, as mentioned, those symbols are generally kind of standardized. So that might be a valve is the little thing in the middle there. A lot of them have tags, which are labels associated with them. And as we'll see in a second, there's some semantic data that we can pull out of those. And the relations between which valve is attached to which tank is controlled by which computer is of interest as well. Tagging is the first thing that we decided to look at because pulling text out of these documents is much easier than trying to understand the actual picture information, at least as a starting point. A lot of these were actually just scans of PDFs, but even those you can at least do OCR, and there's some pretty good tools for that. And these tags, once you have them in text format, you can actually pull some information out of them, and it'll probably look different from site to site, but for sites there is generally a pattern to it. So for this particular standard that they use for this site, it's laid out into which system, which subsystem, which part of that subsystem, and then even has some information about if there's any parallelism and which instance of that item it is. So when we're looking back at something like this, maybe this is like, we can see it's a valve, and maybe it's valve 1 versus 2, and you can see sort of where it is on the thing there. In this case, 84 is maybe it's the electrical system, and ELJ is the code for a junction box, which has something going on. So the first step that we did was we took these docs, we put them through just some standard like off-the-shelf OCR tools, and then you can start doing text search on them. As you noted, or as you might have noted, the tags are very, very standardized, which leads itself well to regular expressions. And so you can write a pretty easy script to say, given a tag, look through all of the documents that we have and find which documents are related to this piece of equipment, because the tag identifies like a piece of equipment. Or given a document, give me a list of all the equipment that it talks about. And we're dealing with a lot of docs usually, so this is something that already can start to narrow down your search when you're trying to figure out what's going on with a particular system. And of course, we've got to use LLMs because those are the new buzzword. And we can use those with especially the more sort of text-based functional documents where it might describe what operating system a computer controlling a valve is using in just like plain text. And so we can start using some, again, off-the-shelf tools like LangChain and like Llama Index just to start building up the graph, which we'll see in a second. Template matching with just like some standard OpenCV stuff can also be used to start matching the symbols in those diagrams. So here's an example of the obligatory LLM. Can the system that is associated with this tag run with one of the meters offline, which is maybe important for your risk assessment? And it says, yeah, we found this document, and the glowing green chemical thing can run even if one of them is off because it's got one built-in spare. And this is really what we were trying to build. And one of the things that I think is most interesting and more broader than just OT sense is that graphs can do a lot for you. There's a lot of really good tooling available around doing queries and doing sort of reasoning and algorithms on graphs. And so we wanted to try to take advantage of that. So the graph that we built had nodes for more traditional IT things like network devices that are running instances of software which is affected by CVEs and are connected to networks. And then from some of the diagrams that we had, like those P&IDs and other similar ones, we can see which physical things they're connected to, which functional assets flow to which. If there's a tank that's flowing through a pipe to a different tank, then if you can affect the upstream one, then that'll have an effect on the downstream one. That's good to know. And from some risk assessments that we found, we also found that we could tie these functional assets to consequences. If the tank holding the fuel is ruptured, then people from the companies have probably done a risk assessment and put like a severity on that of that, there's this a high environmental consequence or something like that. There was still a lot of manual work here, but using some Python, we were able to reduce some of that boilerplate, and then we basically just put it in a commercial, like off-the-shelf graph database. So a lot of this, I think, is not too difficult to reproduce, and I'll have some links at the end to some of the software that's handy if you want to try doing something like this yourself. So a very small segment of the graph ends up looking like this. You can see that we've got the sort of turquoisey nodes are computers. PLC in this case stands for programmable logic controller, which is controlling some robotic arms, a conveyor belt, a self-destruct thing, because we're looking at the Acme TNT factory. It's got to have one of those by law. An HMI is a human-machine interface, but again, basically just a computer that's connected to that network there. And so we can start asking these graphs some simple queries, like if I'm on the HMI, which physical devices can I control? And there's the graph database does that pretty quickly, and it can find us from it translates that from the query down at the bottom there. And so we can see, all right, if I'm on this HMI, I can control the robotic arms, the conveyor belt, and the self-destruct thing. Or if I'm trying to do a risk assessment on a particular piece of equipment, maybe if I'm looking at the self-destruct thing, I can ask the database which IT devices have a path to be able to control this. So you can see how that would be useful for some of these higher, more destructive physical things. We can go even further and tie this to things like consequences from those risk assessments. So if I'm an attacker and I'm on that HMI, I can say, show me the fastest way to cause some kind of consequence that would be bad. But more exciting than that would be to actually set some agents loose on this graph and see what they can find. So with, again, just another simple Python script, you can have it start at one of your computer nodes and have it look for any networks that are connected to that device, other devices on that network, and then find CVEs on those devices which are remotely exploitable through the network, and sort of build up your graph of things that you have control over. And if they have a CVE which gives you code execution, you can keep pivoting from there. If it's a CVE which can cause denial of service, then you can potentially disrupt whatever physical assets are being controlled. And so you can sort of build up this blast radius from each of the devices that you can start from. And if you do this to enough of these, you can start to build up a notion of which nodes come up again and again, and sort of maybe try to pinpoint which specific CVEs are going to be the most impactful to patch. If you can only patch like 3 things, maybe we can find some hotspots in the graph and try to get the most bang for our buck when patching. Because if you run the whole thing and you can see what the most valuable assets are, take a few of the CVEs out and run the whole thing again, you can compare the CVEs in context and actually see how much more secure your network is afterwards, rather than just looking at the like the CVSS score. And there are tools that do this as well. So we built one, but there's also a couple of open source ones from MITRE, which again will be linked at the end of this. And they do basically the same thing. So here's an example of that. We can. I told it that we're looking for routes from the engineering station in this chemical process plant to anything that will have a high environmental cost. And you can see that it finds some devices, looks for the networks on those devices, goes and discovers a bunch of stuff. And eventually it finds the self-destruct flamethrower that's reachable through some steps, gives you the attack path there, exploit the CVE, pivot to this thing, and then you can control it, and it has the environmental consequence of high. This was I think I already sort of went through this verbally, but again, basically if you run this differentially, if you run the whole thing with different aspects in the graph, maybe if you put in like a firewall or if you take out some of the CVEs, then you can see how specifically that'll affect how difficult it is to find these paths and how easy it is to get from a likely entry point like the internet to some sort of unwanted event like a high environmental consequence from something in a risk assessment. But this is still pretty early days. There was a lot of manual work here which we're trying to get down. The diagram parsing in particular is something that still requires a lot of manual labor, and so we're looking into some more computer vision-y things to try to deal with that. Of course, I'm sure there's more we could be doing with LLMs going into the future. And a really big one is connecting to more data sources to deal with drift, because these documents are generally, there are some from when the equipment gets updated, but of course, when you're dealing with systems this big and having contractors come in and whatnot, things are always going to change, and that's not going to necessarily be reflected in the docs. So something that's still to be tested is how close these models actually get to real life. And that's another place where I think it's a good starting point, but you still do want to use those other tools like the site visits and interviews to sort of refine it afterwards. These are basically all the tools that we used in the process, and I'm happy to, if you're interested, go into sort of more specifically how we chained them all together, but I'll just leave that up for a second. SciCat, the one at the bottom there, was the MITRE one that was doing the attack paths, and that's kind of fun to play around with. But the two things that I really want to stress and that I thought was most interesting about this was, one, there's a lot of untapped information in docs, especially when it comes to some of this information that you're not going to find just by doing like a network scan or something like that. And I think that's probably true of some other areas as well, where if you think of all the information that you have available to you when you're solving a problem, frequently there will be some that's a little bit harder to get to, but might give you some good insight. And two, graphs are great for modeling complex systems. There's been a whole bunch of really good open source software made for these, and like theory done on them with algorithms and things. And I think it's a tool that we should not be forgetting in this world of LLMs and neural nets and things. We've got some other tools that are, I think, better suited to some problems. So I want to say thanks to the people that were doing this work with me, and that's all I have for now. So I don't know if I have time for questions, but I'll be sticking around for the rest of the day as well.
No, let's move on, but come see Ian. Thank you, Ian.